Hello everyone, this is Dr. Bijmohan. Today I will discuss the one-dimensional box problem using finite difference method. In this slide, equation 1 represents the Schrödinger equation for a particle in a box. Since V is 0 in the region 0 to L, so equation 1 may also be written as equation number 2. Now let's make the above equation dimensionless by substituting h is equal to x by L, where L has the dimension of length, so that s becomes dimensionless. Now, by following some easy steps, we will reach to equation 3. Consider the case when h cross is equal to 1.055 into 10 to the power minus 34 joule second, m is equal to 9.109 into 10 to the power minus 31 kg, and L is equal to 10 to the power minus 10 meter. This equation can be written as equation 4. Finally, equation 4 can also be represented as equation 5, where each term seems dimensionless. Here epsilon is also a dimensionless quantity, which is equal to capital E upon 3.818 electron volt. For simplicity, we have calculated the theoretical value of energy. Here E1, E2, E3 are three different values of the energy for different value of n. Now let's apply the finite difference method. For simplicity, we will use only 5 interval, that is 6 grid points. So by use of finite difference method, equation number 5 can be written as minus psi j plus 1 plus 2 psi j minus 1 upon del square is equal to epsilon psi j, where del is nothing but the spacing between grid intervals. Now according to the boundary condition of one-dimensional box, the wave function at the boundary must vanishes. So the wave function at S0 and S5 will vanish, and therefore we are only interested to calculate the wave function at S1, S2, S3 and S4. So let's run J from 1 to 4. We will have the set of 4 equations. This is an eigenvalue problem which can be represented by equation 6, where HJI is a Hamiltonian matrix which is defined as 2 by delta square when I is equal to j, minus 1 by delta square when I is equal to j plus minus 1, and 0 at any other points. Now let's write the Python code for infinite potential wave problem using finite difference method. First we will import the important libraries, and then after we will import the input parameters. Then after we will discretize the x-axis via x cell plus delta to x r minus delta. After this, we will create the Hamiltonian matrix. Here, this line represents the off-diagonal elements which has the value minus 1 upon delta square, whereas this line corresponds to the principal diagonal elements which has the value 2 upon delta square. Now, to obtain the eigenvalue and eigenvector, we will use this syntax. This section represents the different parameter used for making the graph interesting. Now, to print energy value as calculated by FDM, we will use this syntax. Finally, we will plot different wave functions appearing in the one-dimensional box problem according to these syntax. So this is the plot of wave function of one-dimensional box. Here we see all the graphs equally matched to the theoretical one. This is the energy value as calculated by finite difference method. Here we see that these values are well matched to the energy values calculated to the theoretical one. In this way, we are able to calculate the required energy values as well as plotting of the wave function of one-dimensional box using finite difference method in Python. Thank you very much.